So good evening, everyone. My name is Shami, and welcome to the week 4 tutorial session. And I'm a PhD scholar at IIT Delhi. And in this week, like you guys have in the video lectures, you guys have studied about these temper distributions and this Fourier inversion formula. And basically, with the help of that Fourier inversion formula and all, we are able to like have an isometry of Fourier transform from L2 to L2, and then how we can elevate those stuff to distributions, and that gave rise to this temper distributions. And after that, like you have introduced the idea, like you have seen the introduction of the idea of the Sobolev spaces. And these spaces are very crucial because these spaces naturally arise when you consider partial differential equation and their solutions. So the solutions has to be in some space, and this Sobolev space turns out to be the very natural space in which they have to lie. Because when we are considering basically we consider the weak formulation of our partial differential equation, and we try to solve it variationally. And when we do that, we have some functional over some space, and those spaces are actually nothing but the Sobolev space only. So these spaces are very crucial, and their basic understanding is very crucial when we're trying to solve partial differential equations through this modern approach. So today, we will solve some questions based on distributions, sample distributions particularly, and then we try to solve some PDEs with help of this theory we have developed of temper distributions and all. So that will be our goal for this week. So without further ado, let's start our problems. So this is week 4. The first question which I like to introduce and would like to solve is have some connections with the stats and probability. So it's a very what's a building block distribution or very distribution which is like very basic and very uh, useful, and it's like ubiquitous in every way you see. So it's all about the normal distribution, and normal distribution, if you can see, it's actually a locally integrable function, and it gave rise to a distribution. And we can also say as to be a function only. So it has a very good property when we consider these functions with some different mean and variation, and with different mean and variation. And when we try to convolute them, the mean and variation are actually they vary in a very nice manner. So let me write. So if I let f sigma and f tau be the normal probability distributions of Gauss is defined by, so f sigma x I'm defining as 1 upon root 2 pi sigma is power of minus x square divided by 2 sigma square, and then f tau x defined as 1 upon root 2 pi tau is power of minus x square to tau square. And what are these tau and sigma? These tau and sigma being the standard deviations of the distributions f sigma and f tau respectively. Then f sigma convolute with f tau Nothing but turns out to be f of square root of sigma square plus tau square. So this is the very nice result. And let us try to prove this, and we will use some of the results which we have seen in either in the videos or in the assignments. Solution. So since these functions are actually locally integrable, we will have convolution in these. In fact, integrable, we have convolution in usual sense only. But we'll use the idea, some of the ideas. The first idea which we like to use is that the Fourier transform of e raised per sorry minus x square at xi. So we know that is nothing but e raised power of minus pi xi square, and this is the first thing which we know. This actually helped in solving this adjoint formula. Moreover, also if we know that if that the we take the Fourier transformation of fx at xi is given by this f at psi, then Fourier transformation of f times kx. So this is a dilation by k. This is nothing but 1 by k f hat psi divided by k, and of course the dilation has to be non-zero. So this is non-zero k. So with these two results, we would like to prove. First of all, what we like to do, we have to prove this inequality. So what we try to do to prove this type of inequality, we use the Fourier approach. So instead of proving this, first we try to prove, like we try to write this in some Fourier terms, and then we will see what can we do. So let us try to evaluate the Fourier transformation of now. Consider Fourier transformation e raised to the power of minus kx square at xi. So we know that the Fourier transformation of minus pi x square is same, but if we have something k instead of pi, so how do we deal with that? This can be written as Fourier transformation of e minus, and this is this can be written as minus pi, and then this can be written as square root of k by pi x whole square at psi. So now this is now in the form of the standard Gaussian function with the pi. But now it is now, as you can see, this is a scaled version of this thing, and we know that the Fourier transform scale thing is this thing, which I have written above. So this can be written as 1 upon square root of k by pi, and then we have f hat. F hat is now we have the same thing, so I'm directly writing it to be the e raised to the power of minus pi, and then xi square, but xi square by k has to be here. So it's like xi by, and then k is now square root of k by pi whole square. So this is nothing but root of pi by k e minus pi square xi square whole divided by k. So this will give us the general Fourier transformation of e raised to the power minus k pi s square. Now in our situation, what do we have here? We have this f sigma is this particular form, right? So let us try to have the Fourier transformation of this thing. We have f sigma as 1 upon sigma root 2 pi e minus x square whole divided by 2 sigma square. And the Fourier transformation of this thing, f sigma at xi 1 upon square root of sigma into 2 pi. And then this e minus x square. So now the k is nothing but 1 upon, so k is nothing but 1 upon 2 sigma square. So this is nothing but square root of pi whole divided by 1 divided by 2 sigma square into e raised to power minus pi square, and this is divide, and so this eventually has to be in multiply form. So pi into 2 sigma square psi square, and this constant will cancel out, and so this actually will end up being just e raised to power of minus 2 pi square sigma square xi square. And similarly, Fourier transformation of tau xi would be e raised to power minus 2 pi square uh, and tau square xi square. So now how to prove the equality of convolution? So what we try to do, we have to solve the Fourier transform thing. So now since we have this thing, if if we see, if we have to see f sigma convolution with f tau has to be equal to f of sigma square plus tau square. So if we take the Fourier transformation on both sides, this will give what? Fourier transformation of f sigma multiplied with Fourier transformation of f tau, and this whole equals Fourier transformation of f of square root of sigma square plus tau square. So this is actually if and only if result, because we can have Fourier inverse applied on both sides. So this is irreversible. So let us try to see what is this product. What is Fourier transform of sigma? This is e raised to power of minus 2 pi square sigma square xi square. And this is the e raised to power of minus 2 pi square tau square xi square. And this is all we are evaluating it by only. This can be e raised to power minus 2 pi square sigma square plus tau square psi square. And what is this? This is nothing but the square of e minus 2 pi square square root of sigma square plus tau square whole square psi square. So this is actually nothing but, if you see, this is the same form we have here. So this is the Fourier transformation of f of square root of sigma square plus tau square. And what was the left-hand side? This implies the Fourier transformation of f sigma convolute with f tau is nothing but Fourier transformation of f sigma square plus tau square. Moreover, these Fourier transformations which are getting, it's again in Gaussian form, so they are again L1. So I can use the Fourier inversion formula. So by Fourier inversion formula, we have basically f sigma convoluted with f tau is equal to f of square root of sigma square plus tau square. So actually, this actually proves the result that which we wanted. So we can see this is a nicer way to show things. We don't really have to evaluate the convolution because sometimes it's really messy. And we can also use take advantage of this particular fact is when we have the Fourier inversion holds, we can just have to show the quality for the Fourier things. Sometimes that is much easier to solve, as we have seen in this case. So that's one method, and that is, I guess, sometimes very handy when you're trying to prove things. So next so that's one also a neat application of Fourier inversion formula. So keep that in mind. And the Fourier transformations are again relevant. We can invoke the inversion formula, and then we have this inversion to be there. So moving on, the next thing which we are basically try to see one question, which is uh, more or less that involves partial differential equations in terms of distributions, and we will see some of the things which are useful when we are trying to solve a PD with respect to distributions. And so it's like one of the first encounters of I would say a PD in terms of distributions, and we try to see some regularity and that type of stuff. And this is very useful because at the end we want solution to be in normal functions forms. We are actually initially we get the solution distribution form, but our goal is to find a function, a nice function, eventually a continuous or a C2 function or C infinity function to be our solution of our partial differential equation. So first we are setting a partial differential equation in a normal format. We take that PD to a distribution sense, and then we try to solve there, but we get solution in terms of distributions. But we want to come back to normal functions because eventually we want solutions in that form only. So to come back to from distribution space to normal solution space, we need some regularity towards these distributions. Eventually, first we try to prove that this distribution actually comes from a function which is an LP function or a pth integrable function, and eventually then after we try to show it to be continuous. When that hold, we then put more regularity in that to show more regularity in the solution. So that's the whole idea to solve the PD. So the next question which you like to see will be based on the idea that that we are actually coming back to the from the distribution to the actual function spaces. So next question based on this particular thing only. So let me write the question. So if I take hue in the temper distribution, such that d4 u dx4 plus lambda u is in L2R, and that holds for all constants lambda positive. Then show that dku dxk is in L2R, 4k in like this 0 to 4. So what we're doing here is U is actually a distribution solution to this partial differential equation. And what we're trying to prove is that all the derivatives up to kth fourth order are actually L2. So that is basically the U is in turns out to be in the Sobolev space W 4 2, right? So 4 is the fourth order and 2 implies since they are L2, that's the integrability. So that's our first wave distribution to the Sobolev space. So that's basically we try to solve in this question. Hello? So what we try to do, that's the first step. So we would like to solve this. So so we will use, so first of all, we have this d4u by dx4 plus lambda u is in L2. And we use the idea that the Fourier transformation is an isometric isomorphism. This implies the Fourier transformation of this thing, this thing, d4u by dx4 plus lambda u. This is again in L2R. Right. But what exactly is this? This is actually nothing but we have seen the formula that when we apply a Fourier transform to the derivative, it turns out to be it's in terms of the polynomial factor multiplied with the Fourier transformation of our original function. This is nothing but iota 2 pi xi whole is power 4 u hat plus lambda u hat is in L2 of R. So this is the property we're just using here. And moreover, we can distribute in the sense because one thing we have to note here, I can take the Fourier transformation separately because I know that since using the user tempered distribution, this implies that dk by du by dxk is also a tempered distribution. So that is the case. So then this I can separate the Fourier transformation and I can write this particular equality. Okay, so far so good. And this is nothing but 2 pi raised power of 4 xi raised power of 4 u hat. We can take the u hat outside plus lambda to u hat in the L2R. And this further implies that you can take the lambda out, lambda times 2 pi raised power of 4 xi raised power of 4 lambda plus 1 into u hat in L2 R. So now one thing that this thing holds for all lambda positive. So in particular, so you take lambda equal to 2 pi raised to power of 4, then and can take this scalar factor out. So this implies that xi raised to power of 4 plus 1 to u hat, this belongs to L2 R, right? So now we like to show, we know that the derivatives uh, in L2, even only if their Fourier transform is in L2, so that is nothing but polynomial times our u hat. So we like to use that idea. So what we try to now show that we claim that for all xi in R, mod xi raised to power of k is less than equal to 1 plus xi raised to power of 4 for uh, sin, so basically k 0 to 4. Okay, so we have to show this. So how we do that? We do by case analysis. So case one, if mod psi is less than equal to 1, what this implies? This implies that of course psi raised to power of k is also less than equal to 1, and that implies that actually and this is less than 1, and that is further less than equal to 1 plus xi raised to power of 4. So for this case, we have the equality, and this actually getting for all k in 0 to 4. The second case will be if mod xi is greater than 1. If that is the case, then we know that xi raised to power of k has to be less than equal to xi raised to power of 4, and that holds for all k 0 to 4. And that actually implies that mod psi k is again less than equal to 1 plus mod xi raised to power of 4. So both cases, combining both cases, we have a claim. Now, finally, what we'd like to show now. So, what this basically implies now, this implies uh, that if as basically if I 2 pi I 2 pi psi this power of k u hat will be in L2R for k in 0 to 4. And since that is the case, so what this actually implies, this can be written as nothing but we know that the Fourier transformation of dku by dxk, this is nothing but iota 2 pi psi raised to power of k u hat. But as we have shown, this is nothing but in L2R. Again for k in 0 to 4, what this actually implies, this implies the Fourier transformation of derivatives are in this, but again the using isometry, we have this dku by dkx is again in L2R for k again in 4, again using the isometry of Fourier transformation. And that basically proves our claim for this. So the again we are heavily use the idea that Fourier transformation is a isometric isomorphism, that idea, and then we continuously changing our real from functions to Fourier transform of the function, and then again using that, and then using coming back to the original function, and we are using this function, this idea a lot of time that the derivative of the Fourier transformation is scalar multiple times the Fourier transformations. These type of stuff is actually we use quite a lot. So moving on, let's have one more question. Again, this on this tempered distributions. So we must know some basic tempered distributions, some basic functions. And when we talk about the basic functions, the very basic function that is the building block of this continuous function, all those functions are the set of polynomials, and that include also again this power function. So these are the building blocks, and we would like to see these are the tempered distributions, and not only that, we can also find their Fourier transformation. Again, they are not integrable, so this Fourier transformation is in terms of distributions only. We cannot actually, they are not in L1, so the Fourier transformation is not defined for this function in the classical sense, but in distribution sense, we can have, we do have a Fourier transformation of the polynomials. So show that every polynomial dx equal to a naught plus a1x anx with real coefficients defines a tempered distribution. Moreover, find the Fourier transformation of px. So actually, so as I told, the distribution, this Fourier transformation defined the distribution sense only in sense of tempered distributions. So as we know, for all fine sparse space, we know phi times px is again in square space for all polynomials. And what this implies? This implies that px times phi actually will be in L1. Cost functions are actually integrable. I can take, in fact, we can take this. This is in L1. So this implies this is well defined. So this is actually integration of R of px phi x dx is well defined for all fine square space. And like the continuous distribution, because if I take any phi n's converging to 0, we have this basically convergence of this integral. this actually defines a continuous distribution. Because eventually we can do this polynomial, if we are taking any polynomial, this is a fixed polynomial. So we can take the sup norm of this phi n's and this px to be out, multiplied with another polynomial and divide by another thing. That thing actually has to go to 0 only. So this will actually give us the convergence. So this then it follows easily that is that what px defines a temper distribution. Defines the temper distribution. So next thing which we like to do this is we have to find this Fourier transformation of this, right? So what we try to do to solve this, first we try to find the Fourier transformation of this power thing because these constitutes the polynomial. And how do we do that? The Fourier transformation x power k can be written as x power k times 1 with the multiplication of function by x power k. And this is nothing but we know that this is minus 1 raised to the power of k, 1 upon iota 2 pi raised to the power of k. And then this is the d by d psi k, so the k derivative over the Fourier transformation of 1. Right, so this is just the formula, just that multiplication can be transferred into this derivative stuff. So finally, this can be again written as now the Fourier transformation one we know is Dirac delta minus 1 raised to the power of k whole divided by iota 2 pi whole raised to the power of k into that dk by d psi k of Dirac delta, and the Dirac delta are actually the dipole functions and those stuff. So this is nothing minus 1 raised to the power of k delta k whole divided by iota 2 pi k. So this is basically the Fourier transformation x to the power of k. Then using linearity of Fourier transformation, then using linearity, we have the Fourier transformation of the polynomial is nothing but a naught of Fourier transformation of 1, a1 of Fourier transformation of x into an Fourier transformation of x to the power of n, and this whole can be written as a naught delta plus a1 minus 1 raised to the power of iota 2 pi delta 1 and whole an minus 1 raised to the power of n iota 2 pi whole raised to the power of n delta n. This is actually the value of our Fourier transformation of the polynomial. Okay. Next, what we would like to do, we are interested in, like we have found the Fourier transform many temper distributions. So next, we would like to evaluate the Fourier transformation of one that particular type of distribution, which is quite peculiar in nature, and we have seen that it was a like in general it wasn't a distribution because it wasn't a locally integrable function, but we make it to be a uh, distribution by like considering the principal value. So yeah, you guessed it right. The function which you're talking about is the principal value of the 1 by x. So this was turns out to be distribution and we put the principal value. So we will see, like, we would like to see the Fourier transform of this particular function distribution. Okay, so let's So find the Fourier transform of t is equal to Cauchy principal value of 1 by x. We saw in our previous tutorial that it turns out to be distribution. So we would like to calculate this, calculates Fourier transform. So actually this turns out to be a temporal distribution. That's not an hard tough deal to prove. One can prove it to be temporal distribution. And moreover, there's one more thing which I like to mention that this is an odd distribution. What do I mean by odd distribution? So it's like its roots are like motivated from the odd function only. So one can we have that sort of similar notion for the distributions as well. So that turns out to be the case is that we can have one such notion of odd and even distribution. So we can define and moreover these are like very analogous to this odd and even functions, and eventually you can see if I take any element law function which is even or odd, then it we give rise to one distribution, and that again turns out to be matches with the definition which we are going to give. So let me write just one definition first. We will be requiring this. So T is a distribution is called odd if and only T of 5 reflection is T of minus T of phi, where phi reflection is nothing but phi of minus x. And this holds for all phi distributions. So this is the definition of distribution to be odd. And one thing we can actually prove that this Cauchy principal value is an actually a odd distribution, which I am leaving as an exercise that you guys can try. It's not in hard to prove. So if we have a distribution, then that Fourier transform which is an odd distribution, then Fourier transform also turns out to be an odd distribution. So one can show that this Cauchy principal value of 1 by x, this turns out to be an odd distribution or tempered distribution. And finally, one more thing which we would like to see that also for any phi in cross space that we have considered x times Cauchy principal value of 1 by x into phi. So this is actually this bracket actually means this if let me not write in bracket terms, maybe confusing it will be. That is the distribution generated from Cauchy principal value of 1 by x. So we know that x t at pi is nothing but t of x pi. This is the definition of multiplication by a singularity function. And what is this? This is nothing but limit at ln tends to 0. On the positive hand side, mod of x is greater than or equal to epsilon x pi whole divided by x. dx. But this is nothing but limit at epsilon tends to 0 from the positive hand side of mod x greater than equal to epsilon phi dx, but phi is a sparse function. This is nothing but just integral over R only. And this is nothing but the distribution generated by 1 only. So this can be written in terms of T1 phi, where T1 is the distribution generated by phi. So basically, what do we have here? We have here this x dot t is the one identity function of T1 function in sense of distributions as well. So we can take the Fourier transformation because we are in tempered space, so tempered distribution space. So there's the Fourier transformation of xt has to be equal to the Fourier transformation of 1 only. Now, the fact we are now using it that x, if you take the Fourier transformation of x times a distribution, this is nothing but the derivative of the Fourier transformation of the distribution. So this implies this is nothing but minus 1 whole divided by iota 2 pi, and this is nothing but the dy dz. So this now turns into a derivative, the order of 1 only, because we have only one factor of Fourier transformation of t. What is Fourier transformation 1? 1 is just this is Dirac delta only. Now, what can we write this as? This is dy dz of Fourier transformation of t, and this is nothing but minus iota 2 pi delta. But Dirac delta, we know that this is nothing but Dirac delta is at 0, is nothing but the derivative of what? This is the derivative of Heaviside function. So now this is the Heaviside function. Now this can be written as the d by dz of Fourier transformation of t plus iota 2 pi h z equal to 0. Now, as we know that this is tensor distributions, but since you know even the distributions in even if it's 0 in sense of distributions, this thing has to be what? The Fourier transformation of t has to be nothing but um, what? It's minus iota 2 pi Heaviside function plus c for some constant c. So now our whole task now left with just we know the Fourier transformation of t is this thing only, but we have to also evaluate the value of the constancy as well. And once that is done, we have this basically the Fourier transformation of a Cauchy principal value. Now to evaluate this constant, what we try to do, we try to do this uh, basically we need to evaluate this constant. So what we try and know that is an odd distribution. And what basically this implies? This implies, like you guys can prove why, that Fourier transformation of T is turns out to be again an odd distribution. So once that is the case, we can employ the definition of odd distribution. And what is that? That is that if I take the uh, this T of phi cap, this turns out to minus T phi. So using this, what we end up with, but one thing which we like to note that is that this ft is a Heaviside function times some constant. So this implies, but ft is a function, and again you guys can show that this will imply that ft is an odd function of xi variable. So what this implies, the Fourier transformation of t at xi has to be equal to Fourier transformation of t at minus xi, and this has to be all minus. Now what this basically implies that we know that Fourier transformation of t is given by this thing only. So this is minus iota 2 pi Heaviside at xi, and then some constant is there, and this is minus of plus of minus iota 2 pi Heaviside of minus xi, and this will give me a minus constant. And this whole gives me one thing. It gives me, this gives us basically the 2c is nothing but 4 iota pi, which 2 iota pi only, 2 iota pi of Heaviside of xi plus Heaviside of minus xi. So what is Heaviside of xi plus Heaviside of minus xi? This actually is nothing but it's one constant, one only. So it is identically one only. So that will imply the constant is nothing but iota pi only. And since this is constant, this thing only, thus we have the Fourier transformation of t, which is nothing but the Fourier transformation of the Cauchy principal value of 1 by x, nothing but minus iota 2 pi Heaviside function plus iota pi. And like if you try to like bifurcate this thing, this is nothing but minus iota pi for xi positive and iota pi for xi less than 0. So this turns out to be actually the Fourier transformation of our Cauchy principal value of 1 by x. So it was like again not so hard question, but again used a little bit of fact of this odd function, like I have explained here. Apart from that, this is just like using again to get identity. Whenever we are in tempered distributions function, our just main idea is to use this Fourier transformation on and use the knowledge of the Fourier transformation things, and then once we get some knowledge there, we get back to our original temper distributions, and then we get information for that. So yeah, so that's quite helpful, and it actually gives us very nice results if you can see here. So the convolutions first question we did, and then after those questions, so yeah, it's a quite a nice technique to get some very good results. So that was one thing. Now moving on, next what we would like to do, we would like to uh, have one again uh, partial differential equation which has we try to solve the temper distribution solutions, and then we see that how can we associate that uh, temper distribution equation with its corresponding equation with respect to the Fourier transformation. And we see that the same type of notion actually are used in solving the heat equation. So heat equation is actually solved by this Fourier transformation methods only, and it's very powerful. So it gives actually rise to this heat kernel and kind of stuff, and leads to a lot of theory. So let's start with this question. It has two parts. The first we would like to do that find the temper distribution solutions of du by dx plus lambda x cube equal to 0. Nest the shape for real lambda to be non-zero. So first of all, let us try to solve this distribution equation in time. So to find the temper distributions. So how do we do that? So this is actually can be seen as so T. We are interested in finding the temper distribution solutions of this du by dx plus lambda x equal to 0 in the temper distributions, and for our real lambda in R. So since I know this is just linear first order equation, so then the usual solutions actually comply with the distribution solutions. So ux will actually uh, given by this uh, exponential of minus of integration of px dx being the coefficient of u. So this is lambda x. So this will actually give me that ux is actually only c raised to power or c times c raised to power minus lambda x squared by 2. So now we have to check whether this actually generates a temper distribution or not. So we just only need to check whether this graph is temper distribution or not. So if my lambda is positive, this then definitely this thing will is e raised to power minus lambda x squared by 2, which is the L1 function. And then being this is an L1 function, so this will be a temper distribution. And since this is a temper distribution, we are done in the case. Whenever but if my case is lambda equal to 0, then this lambda is 0, then this again you will turns out to be an identically a constant function, and that is the L infinity function. And this being an L infinity function, this actually turns out to be a temper distribution. because I know that any integration of any cos space function is actually finite only. So this is actually a temper distribution. So for the case lambda positive, my u is e raised to power lambda x square by 2. And if I take phi 2, we e raised to power minus lambda times x square by 4. This being a Gaussian function, this actually has a very exponential decay and more than Gaussian decay. This actually lies in the cos space, and we have seen this in the videos. So, so if we assume that if I take tu to be the distribution generated by u, if this distribution is actually a tempered distribution, then you must have this tu at phi should be finite. And it is tu at phi, this is nothing but the integration of all over r of u and times phi. But what is this? This is actually 10th integration of e raised to power lambda x square by 4. But definitely this is not finite in our case, so this will imply u is not a tempered distribution. And since it's not a tempered distribution, this cannot be a tempered solution for our equation. So why we are like interested in a distribution to have to be tempered distribution? The benefits of this is actually sometimes when we are not in a position to like directly calculate the Fourier transformation of function, but I know that this function has a Fourier transformation and can be seen as a distribution, tempered distribution. So since I'm able to see this that as a tempered distribution, I know that function can be seen as a solution of some OD, and that OD I can apply Fourier transformation and convert that OD, translated OD to another OD, in which the solution is actually nothing but the Fourier transformation of our original function. And sometimes that OD are very easy to solve, and this actually will, when I'm able to solve easily, I will actually get the Fourier transform of our original function, and that is very easy to solve. That is actually we are not able to first priorly able to solve directly, but this is one way in which we actually go to the OD and then try to solve the transform the OD and finally get the Fourier transformation of original function. It is something very useful and handy in nature, and that what we will see here in our case. So, I will try to find the differential equation satisfied by the u hat, and then we saw what is the value of u hat. So we know that for lambda non-negative, fu was well defined, so we can only talk about distribution solutions, tempered distribution solution in this case only. And we would like to use the standard result that the Fourier transformation derivative is nothing but iota 2 pi xi Fourier transformation u, and then Fourier transformation xu is nothing but the minus 1 upon 2 pi iota, the derivative of fu. So this is our OD, and we just apply Fourier transformation both sides, and we eventually get with this equation. And after that, this is just a first order OD which can be solved directly. So after solving this directly, we are getting that this is actually nothing but one times some exponential of this thing, which is something which is again having a Gaussian decay. So it will lies in again cos distribution, and this requires lambda to be non-negative because lambda is the denominator. So we have to separately consider the case for lambda equal to 0. In this case, we are not no longer having this derivative term with respect to xi. So it will be just 2 pi iota xi times u hat equal to 0, or just xi u hat equal to 0, but xi is 0 at and then we have done some question that was that x minus a times some distribution equal to 0 if and only if something happens. So that is the same thing. This will give it to give rise to that u hat has to be of this form c2 times delta, which delta is the Dirac delta distribution, and it's used to any general constant, and this is my value of my u hat. Okay, so that's all for this lecture, um, and with this, I end my session for this week. Thank you all. Uh, and yeah, that's all. Bye.